Hello everyone, welcome in Learn CHE. Here we are with our 10 MCQ series, and today we are going to discuss about chemical reaction engineering 10 MCQ series, right? So before starting the video, if you haven't subscribed Learn CHE YouTube channel, you can subscribe it for upcoming more beneficial videos for you. And if you haven't joined Learn CHE social media handles, you can join and you can ask your doubts and inquiry there as well. So let's jump into our first question. So our first question is alpha plus beta in the rate law is known as the, okay, and here are four options. The first one is order of reaction alpha plus beta. What is alpha plus beta in the rate law? Is it order of the reaction or overall order of the reaction, molecularity, or none of these? So before solving this question, first of all you should have know about what is rate law, right? So what is rate law? Suppose this is our one reaction, A plus B is converted into C plus D, right? So this A plus B is a reactant and this C plus D are the product. Now what will be the rate law? Suppose if I am writing about the rate law with respect to A, so it will be minus RA is equal to K CA power alpha and CB power beta, right? So this is the rate law. So this alpha and beta, what are these? These are the power of concentration A and concentration B, right? And this is a order of reaction of particular reactant. I can say that alpha is a order of reaction of component or reactant A, and beta, that is beta is a order of reaction of reactant B. This alpha and beta tell us how rate is changing with the concentration of the species, okay? And if I just write alpha plus beta, then it will be known as the overall order of reaction, okay? If we are taking alpha and beta individually, then we can say that these are the order of reaction, okay? If we will take it as a sum, then we will say this is the overall order of reaction. So right answer will be overall order of reaction, not order of the reaction, right? So this is the answer of first question. Now for the second question is, for an ideal plug flow reactor, the value of Peclet number is, okay? First of all you should know what is Peclet number, okay? And after that you can solve the question. So here are four options. The first one is 0, second one is infinity, third one is 1, and the fourth one is 0. So in the case of ideal PFR, okay, in the case of ideal PFR, before that you should know about the what is Peclet number, okay? So Peclet number is a rate of transport, okay? It is the ratio first of all, and it is a dimensionless number, and it is the ratio of rate of transport by convection divided by rate of transport by diffusion, or we can say the dispersion, right? And it is the reciprocal of dispersion number. Suppose this is my dispersion number. What is dispersion number? Dispersion number is D by UL, right? And if I reciprocate it, then it will become the Peclet number. This is my Peclet number, okay? So what will be the Peclet number if I talk about the only simply Peclet number? So Peclet number will be UL by D, right? So in the case of, I just told you about the ideal plug flow. In the case of ideal plug flow, no dispersion is involved, right? So there is no dispersion. Why? Because the flow is like that in the ideal plug flow case, right? So this is the flow. That's why there is no dispersion. If there is no dispersion, or we can say that if there is no dispersion, then this portion is going to be 0, right? Then what will be the Peclet number? Peclet number is going to infinity, right? So option B is the right answer. And we can also define dispersion number as well for the ideal plug flow. Okay, please let me in the comments box what will be the dispersion number for the ideal plug flow in this case. Okay, now here is the question for you all. Please let me in the comments box what will be the right answer of this question. This is a very simple question. The question is, chemical reaction engineering is the study of rate and mechanism only, rate only, designing only, and the D option is chemical kinetics and design of the reactor. Right? So you have to choose one answer and you have to tell that what is the right answer in the comments box. Okay, chemical reaction engineering, one of the core subject of chemical engineering curriculum or chemical engineering branch, because this is the only subject which separate chemical engineering branch from other branch. Otherwise, when we study other subjects like mass transfer, heat transfer, thermodynamics, fluid mechanics, they are also taught in other branch as well, right? But chemical reaction engineering or reaction engineering is only studied in the chemical engineering. So please let me in the comments box what will be the answer of this question. Now the third question is, zero order reaction gets completed in. Okay, here are the four options. The first one is infinite time, the second one is finite time, the third one is depends upon calculation, or fourth one is none of the above. Okay, so before solving this question, I am just telling you the formula. What is the formula? The formula is minus Ra, that is the rate of reaction, is equal to minus dCA by dt, okay, equal to K. Okay, we write C, right? So in the case of zero order, what will be the power of its? 0. Okay, and Ca power 0, what will be this? This will be 1. Okay, so I can write simply K here. Okay, this is a simple formula to represent the rate. Now I rearrange it. Okay, so what I'll get minus dCA is equal to K dt. So right, when I'll integrate it, so what I'll get? Minus dCA, K is a constant, so it will go outside, dt. Okay, so what will be the limit? 0 to t in the case of time, or here what will be the limit? Ca naught means initial concentration to final concentration. So here you can see that what will be the answer? The integration of dCA is Ca. Okay, so I am just simply writing Ca. Now what is the limit? Limit is Ca naught to Ca. Then here is the minus sign, equal to K T. Okay, now if I solve this, so what I'll get? I'll get Ca naught minus Ca equal to Kt. Why? Because listen, B minus A. Okay, so Ca minus Ca naught, when I multiply this minus sign, so it will become Ca naught minus Ca is equal to Kt. Okay, so what is asking here? Zero order reaction gets completed. Okay, so when, okay, before that, okay, so this is a Ca naught minus Ca is equal to Kt. Now what I have to do? I can simply write Ca naught minus, what can I write Ca? I can write Ca as a Ca naught 1 minus Xa. Okay, I can write this Kt, right? So Ca naught by Ca naught will be cancelled, and when this minus will go, so it will be multiplied and it will become Ca naught Xa is equal to Kt, right? So what will be the time? Time will be here Ca naught Xa by K. Okay, so this is the T is equal to Ca naught Xa by K. Okay, and what is asked in the question? Zero order reaction gets completed. Okay, so when the reaction will complete, then this XA will become 1. Okay, now what will be the answer? Answer will be the T Ca naught by K. Okay, what does that mean? It means that T, that is a time for the zero order reaction completion, right? What is that? That is T is equal to Ca naught by K, means this is a finite time. Okay, and I would like to tell you that zero order reaction, or the reaction which has a order less than 1, which has a order less than 1, okay, these order reactions completed in a finite time. Otherwise the first order and above first order reaction gets completed in a infinite time. Okay, they never completed in a finite time. I hope you understood this question. Now the fourth question is, the extent of a reaction is. Here are the 4 options. The first one is different for reactant and product. Second one is dimensionless. Third one is dependent on the stoichiometric, and the fourth one is all the above, right? First of all, you should know about what is extent of reaction. Okay, so suppose this is my one reaction, that is A plus A, B plus B, that's converted into C and D, right? This small a, small b, small c and small d are stoichiometric coefficient. Capital A and capital B are the reactants, and capital C and capital D are the product. Okay, now we have to find the extent. Suppose I denote extent by N. What will be that? It will be initial number of moles of A minus final number of moles of A divided by its stoichiometric coefficient. Okay, then it will be equal to initial number of moles of B minus final number of moles of B divided by B. Then it will be equal to initial number of moles of C minus initial final number of moles of C divided by C, and it will be equal to initial number of mole of D minus final moles of D divided by D. From here you can say one thing. What is that? Different for reactants and product. The extent of reaction is not different for reactants and product. They are same. Okay, so this question is wrong. That's why this question is also wrong. Okay, now we have two options. First one is dimensionless and the second one is dependent on the stoichiometric, right? So it is not dimensionless. It has a unit of mole, right? So that's why the answer will be dependent on the stoichiometric. So right answer will be C, right? Now the fifth question is, an exothermic reaction takes place in an adiabatic reactor. Okay, the product temperature dash the reactor feed temperature is equal to, first option, second option is always greater than, third option is always less than, and the fourth option is maybe greater or less than. Okay, let's solve this question. This question is also good one. Okay, whenever you solve these type of question, it's improve your concepts. So okay, this is my reactor adiabatic, where what is saying that this is an exothermic reaction. Okay, so suppose this is my feed and this is my product, right? So and this, because this is an adiabatic reactor, so means heat loss will be 0 here, right? So suppose this is the my adiabatic reactor, and because the reaction is exothermic, in the case of exothermic, heat release or energy release during the reaction, energy release. Okay, so suppose if there is the temperature is T1 and here is the temperature is T2, this is a feed, okay, and this is a product. So if suppose this is the feed, okay, and because this is a exothermic reaction, so heat will release or heat cannot go outside. Why? Because this is a adiabatic reactor. That's why the temperature of product will be always greater than the temperature of feed, okay, or we can say the reactor feed temperature, right? So what will happen here, the product temperature is always greater than the reactor feed temperature, okay. That's why the answer B will be the right option, okay. And suppose if there is a second case and this is the reactor, same that reactor is also an adiabatic reactor, but in that case there is one thing. What is that? The reaction is not exothermic, the reaction is endothermic. And in endothermic reaction, what we do, we provide energy or heat, right? So in that case, what will happen, the temperature of reactor feed temperature will be greater than the product temperature, right? In the case of endothermic, or this is the case of exothermic. That's why the option B is the right option. Now very good question. The question is, what is the percentage of reactant A remaining after 6 half-life? Okay, here are the 4 options. The first option is 2.98, second one is 3.76, third one is 8.98, and the fourth one is 1.56. Okay, so suppose initially I have a reactant and that has a concentration Ca0. Okay, after that it becomes Ca0 by 2, because I have to talk about the half-life, right? Then it will goes into the Ca0 by 4, then it will go Ca0 by 8, then it will go Ca0 by 16, then it will go Ca0 by 32. Okay, so here you can see that this is the first case, this is the second case, okay, this is the third one, and you can say the third life, this one is a fourth and this one is a fifth. Okay, now it will go from Ca0 by 32 to Ca0 64. Okay, so what is the percentage of reactant A remaining after 6 half-life? That is Ca0 by 64, and we have to find the percentage. Then what will be the percentage? Please let me in the comments box. Okay, I am writing here the formula, that is Ca0 by 64, that is the final, divided by initial. What is the initial? Initial is the Ca0, okay, into the, okay, to find out the percentage. Now what will be the answer? Please let me in the comments box. And this type of question you can find by the another method. The method is this Ca0 and this Ca0 is cancelled out, right? And here is a 64. Okay, can I write this 64 as a 2 power 6? Yes, I can write. Then what will be here? 1 by 2 power 6, okay, into 100, if I have to find the percentage. Okay, because here is the, we are talking about the 6 half-life. Okay, suppose if there is the n half-life, then I can simply write 1 by 2 power n into 100. Okay, this is the case when someone asks you about the what is the percentage of reactant A remaining after the n half-life, then you can find by this method as well. Okay, I hope you understood this question, and its answer will be 1.56. Please let me in the comments box whether you are getting this answer or not. Now the 7th question, very simple question. The ratio of volume of a reactor to volumetric flow rate of feed at inlet condition is called. Okay, this is the volume of reactor. Suppose volume is V and the volumetric flow rate, suppose volumetric flow rate is Vi, because we are talking about the initial condition, right? So what is the unit of volume? The unit of volume is cubic meter. Yes, I know. What is the unit of volumetric flow rate? Its unit is cubic meter per second, right? So that will be cancelled and the unit will come into the second. Okay, and that unit is velocity? No. Residence time? Okay, we can hold it. Okay, the velocity will not. Now we have only 2 options. The first option is average residence time and the space time. So right answer will be the space time. Okay, now eighth question is, the half-life of first order liquid phase reaction is 30 seconds. Then the rate constant in per meter is, okay, we have to find the rate constant, that is K. Okay, what we know the half-life, right? What is the formula? First of all, we should know about the formula, and in the case of first order, here is the one formula. The formula is Ca into Ca naught e power minus kT. Okay, this is the formula, right? So for the half life, what I can write, the Ca can be written as Ca naught by 2, because in the case of half life, the concentration, final concentration becomes 1 by half of the initial concentration, right? And here is, this is a Ca naught e power minus k. Okay, then this t will become, okay, now you have t by 2, right? Now what you have to do, this Ca naught by Ca naught, that will be cancelled. Now you can simply find the value of k by using the log property. Okay, this is the this question is not tough, and you will get your answer very easily. Okay, otherwise if you are getting this question tough by this method, you can simply find the answer by the method of, by simple writing minus Ra is equal to minus dCA by dt is equal to kCA. From this method you can also find out the value of k, because here you can put Ca as a Ca naught by 2, and this t, when you will solve this t by the integration, and this t can be taken as a t by 2 or equal to 30 seconds, right? Now the ninth question, the vessel dispersion number for an ideal CSTR. This term is very important, that is ideal then CSTR. Okay, so we discussed about the dispersion number. What is dispersion number? Dispersion number is D, that is a dispersion, or we can say the diffusion, divided by UL. The U is a velocity and this L is a length. Okay, in the case of ideal CSTR, okay, in the case of ideal CSTR, and here is the ideality. What is here? Here is the ideality, and this D tells us about the, okay, the rate transport by the dispersion or diffusion, right? And this portion mu UL, this tells us about the convection. This tells us about the convection. That's why here this term is going to be 0 and the dispersion number will becomes infinity in the case of ideal CSTR. So what will be the right answer? The right answer is going to be infinity. Okay, in the case of ideal CSTR, the dispersion number is infinity, but in the case of ideal PFR, the dispersion number is a 0. Okay, now the next question is, the rate of reaction is the number of moles disappeared or produced per unit dash per unit time in a homogeneous mixture. What is the meaning of homogeneous mixture? Homogeneous mixture is also known as the uniform mixture, okay, where the only one phase is present, right? So this is the general formula of a minus Ra. Okay, we have written the formula of minus Ra. So this is the general formula of a minus Ra. What is the definition of rate of reaction? It say that the rate of reaction is the number of moles disappeared or produced, means it is defined for the reactants as well as products as well. Okay, disappeared per unit dash per unit time per unit volume. So the right option is volume. Okay, per unit volume per unit time. That's why the unit of rate of reaction is mole per unit volume. Suppose I am writing liter into the time. Suppose I am writing here second. Okay, so this is the right answer B. So today we discussed about the 10 MCQs of chemical reaction engineering. If you have any doubt in any question or you have any suggestion, you can let me in the comments box. Okay, so if you haven't joined Learn CHA YouTube channel, you can join, and you can also join our other social media handles as well. Okay, so thank you for watching. See you soon.